Hi, this is Mrs. Westmoreland, and today I'm going to talk about electrolytic cells. So these are the kind of electrochemical cells in which we use electricity to cause a chemical change to occur. So first let's make a little comparison between an electrolytic cell versus a galvanic cell, the ones we have been talking about for several days in class. So a galvanic cell is a battery, but an electrolytic cell needs a battery to operate. A galvanic cell produces electricity from a thermodynamically favorable chemical reaction, whereas an electrolytic cell uses electricity to get a reaction that is not thermodynamically favorable to occur. And also, just on a practical sense, the galvanic cells usually separate the two half cells into two separate containers, while electrolysis is often done in a single container. There are a few things that apply to both types of cells, and these are the things that we've sort of learned mnemonic devices to remember. Oxidation is going to occur at the anode, reduction is going to occur at the cathode, and electrons are still going to flow from the anode to the cathode in both types of cells. So some of the things electrolysis is used for is for separating metals from their ores, so kind of purifying a metal, and also in electroplating, so plating one metal onto something else. So the questions you're asked about electrolytic cells are quite different than the ones about galvanic cells. In electrolytic cells, pretty much the only types of problems you'll encounter are ones in which you're asked to predict the products that will be formed at the anode or the cathode, and also to calculate how much metal will plate out in a certain amount of time, or how much time it will take to plate out a certain amount of metal. So first, let's tackle predicting products of electrolysis. And there's kind of two kinds of these problems as well. So if you are applying electricity to a molten, and whenever I hear the word molten, I think of molten lava cake. So molten means hot, like lava. And so this would be a melted ionic compound. In those cases, the only things you have in the container are cations and anions. So the cation is going to be reduced to a solid metal at the cathode, and the anion in this case will be oxidized, usually to a non-metal element, often a gas, at the anode. So here's an example. We have molten nickel 2 chloride being electrolyzed, and we're supposed to write the reaction that is occurring at the anode or the cathode, and also say what visible changes will it be observed. So as we said, the cation of the ionic compound is going to be reduced at the cathode. So the nickel 2 plus ion, that's part of the compound, gains 2 electrons and turns back into solid nickel metal. And so you would see a silvery metal form at the cathode. And then the anion is going to be oxidized in electrolysis at the anode. So the chloride ion, the negative ion of the ionic compound, is oxidized, changes from a -1 oxidation state to a 0 oxidation state in the gas, the free element. And so therefore, since it's a gas being formed, you would see bubbles. And in this case, the chlorine gas is sort of a pale yellow. So essentially, the overall equation is that we have liquid salt, nickel 2 chloride, and it is being separated into its elements, into the solid nickel and the chlorine gas. So electrolysis, the lysis part of that word really just means to split or to break apart. So we're splitting apart the compound and turning it back into its elements. So this is a pretty not normal thing to occur. Normally, metals and nonmetals combine to form compounds quite readily and easily, but the opposite requires energy to be put in. And really, this only is going to happen when the compound is molten in its liquid state, which occurs at about 1000 degrees Celsius. So that's the only time that the ions are free to move around and therefore migrate independently to the anode and the cathode in the cell. So molten ionic compounds is probably something you've never actually seen in real life. But you have seen a lot of aqueous solutions of ionic compounds. So if we try to electrolyze a solution of an ionic compound, there's also water in the container, and the water can also be either oxidized or reduced. So we can use the reduction potentials to predict whether the water will react or whether it will be the cation and the anion of the ionic compound. So here's an example of that. So if we have, instead of molten nickel 2 chloride, if we have an aqueous solution of 1 molarity nickel 2 chloride being electrolyzed, we want to write the reaction of what is occurring at the anode and the cathode, and we want to also talk about the visible changes that we would see. So we need the following information, which is the reduction potentials for each one of kind of the 4 possible changes that occur here. So we still have the chloride and the nickel, but we also have the water involved. And water can be either oxidized or reduced. So for our 2 choices for reduction at the cathode, we either are going to reduce the cation at the cathode, like we did in the molten example, or water will be reduced. So the reactants are our 2 possible choices that are in the solution. Nickel 2 plus ions and water molecules are in the solution before we apply electricity. And so when the water is reduced, if the water would be reduced, it would change the H plus, the positive 1 oxidation number of the hydrogen in the water molecule, to an oxidation of 0 when it forms the hydrogen gas as a product. But in this case, since the nickel reduction potential is closer to 0, it takes less electricity to cause that change. Therefore, we will see the same silver metal forming at the cathode that we did in the molten example. We also have 2 choices for oxidation. Notice that I've changed these 2 equations to the oxidation direction from the way they were in the first table. The only choices for oxidation in an aqueous solution of an ionic compound are the anion or water. So those have to be on the left side of the arrow. They're reactants. They're the only things in the beaker. The water, the chloride ion, the nickel 2 plus ion. So again, we're going to compare these 2 voltages, but in this case, since the water oxidation potential is closer to 0, it takes less electricity to cause that change to occur, and therefore we'd see bubbles of a colorless gas, the oxygen gas that's forming at the anode, instead of the yellowish chlorine gas. And so this oxidation is taking oxygen from a -2 oxidation state in the water to a 0 in the oxygen gas. So in summary, it's best to figure out what species, which could be ions or molecules, are in the container. These are the reactants of your half reactions. So write your half reactions, which will most often be given to you in the reduction direction, so that only the things that are in the container before the electricity is applied are on the left side of the arrow. Then you compare. You're going to have maybe some choices. 2 that are oxidation, 2 that are reduction, and whichever one of the pair is closer to 0, that takes less electricity to put in to cause that to occur. Therefore, that's the reaction we're going to see. So finally, we have calculations of time and mass in electroplating. And so there's an equation on your formula sheet that is I, capital I, is equal to Q over T, where I stands for the current. So this is in amperes, but an ampere is also equivalent to a coulomb per second. And because it's equivalent to a coulomb per second, a fractional unit, we can use it like we do density or molarity or many other things as a fraction style ratio in stoichiometry. Q is going to be the charge in coulombs, and T is going to be the time in seconds. But most of the time I don't think of these as a equation type of calculation, I do them more stoichiometrically, just thinking about the equation in order to set up my fraction-style ratio for the current. So we've got kind of essentially two directions in which the stoichiometry is going to go. You're going to be either asked, how long will it take to plate a certain mass? So we'll take the mass to the molar mass, and the moles of the metal to the moles of electrons required to reduce the metal cation to the solid metal in the half reaction. Then we're going to use Faraday's constant, again as a fraction-style ratio, to find the charge, and then we're going to use the current as a fraction-style ratio to relate the charge to the time. The other option is to go from time to mass, so taking the time and then using the current as a fraction-style ratio, relating time to charge, then using Faraday's constant as a fraction-style ratio, relating charge in coulombs to moles of electrons, then relating moles of electrons to moles of metal using the half reaction, and then finally using the molar mass. So here's an example, the same one that's exercise 9 in your packet. How many minutes must a current of 5 amps be applied to a solution of silver plus 1 ion to produce 10.5 grams of silver metal? So I start with my mass of 10.5 grams. I use the molar mass of silver to get the moles of silver. And then I use the half reaction to figure out how many moles of electrons does it take to change Ag plus to Ag solid. Then I use Faraday's constant as a fraction-style ratio to relate moles of electrons to charge, and then the amps to relate the charge to the time, and then finally this time is in minutes, so I just converted from seconds to minutes as a final step. So a couple things to remember in these problems. You want to make sure that you change the amps into coulombs per second, so it can be used as a fraction-style ratio. And finally, you want to have the reduction half reaction so you can see in a mole-to-mole ratio how the moles of metal relates to the moles of electrons. In this case, there being 1 mole of electrons for every 1 mole of silver metal that is plated. Thanks for listening. See you in class.